Okay, so this is the chapter 16. So first question is, for the following proton transfer reactions, use figure 16.4 to predict whether the equilibrium lies to the left, which means Kc less than 1, or to the right, which means Kc larger than 1. The equilibrium is about sulfate plus hydrogen phosphate produce hydrogen sulfate and phosphate. So we learn for acid-base reactions, the equilibrium favors the weaker acid, weaker base side. And for this given equilibrium, sulfate and HPO4 2 negative aqueous produce HSO4 1 negative, then PO4 3 negative. We first identify who is the acid and base on the left side and who is the acid base on the right side. So we know on the left side the base is sulfate, the acid is HPO4 2 negative. On the right side, this HSO4 1 negative is the acid and this PO4 3 negative is the base. Why? Because going from left to right, this SO4 2 negative accepted a proton from this one, become HSO4 1 negative. So therefore, this SO4 2 negative accepted a proton. Accepted proton is the base. And this is the acid because going from this left side to the right side, this acid because this donate this H+. And for the reverse reaction, which means going from this right to the left, and we can see this PO4 3 negative is the base because PO4 3 negative become HPO4 2 negative. So therefore, going from this right side to the left side, the PO4 3 negative accepted H+, accepted H+, or accepted proton means the base. So therefore, once we know which is S, which is the base, and we can use this figure 16.4, which will be given on the exam, and we can see in this figure, on the left side are those acid, on the right side are those base. We can compare either the acid or the base. So let's compare, for example, the base. So the base we compare this SO4 2 negative with this PO4 3 negative. So we can see this on this picture, SO4 2 negative is near the top, and let me highlight. So this SO4 2 negative is right here, and then this PO4 3 negative right here. Then we know the base going from top to bottom, the strength increases. So therefore, this one on the top is weaker. So therefore, SO4 2 negative is weaker than PO4 3 negative in terms of the base. And we know the equilibrium will favor the weaker side. So therefore, SO4 is a weaker base on the left side. So therefore, the equilibrium favors the left side, which means the K smaller than 1. So the answer is A. If you want to compare the acid, and you will get the same conclusion because from this table or figure 16.4, we know this HPO4 2 negative is a weaker acid than HSO4 1 negative, and this HPO4 2 negative is on the left side. So again, the equilibrium will favor the weaker side. So therefore, the K is smaller than 1. The answer is also A. Okay, for the next question is about in a certain acidic solution at 25 degrees Celsius, we are given H+ concentration is 200 times greater than OH1 negative concentration. Then ask what is the value of hydroxide for this solution. So then we can say from the statement H+ is 200 times greater than OH1 negative, we can write up the following equation. So the word is means equal. So therefore we have this equation. The equation is H plus concentration equals 200 times OH minus concentration. So we call this our first equation. And we also know at 25 degrees Celsius, the concentration of H plus multiply or times the concentration of OH equals 1.0 times 10 to the negative 14. We call this second equation. Substitute this H into this equation, which means this H from the first equation into this second equation, we get this new equation. So that become this second equation become 200 times OH1 negative. So this 200 times OH1 negative simply come from this first equation. And so therefore in the second equation we say H plus concentration times OH1 negative concentration become 200 times OH concentration times OH concentration. And that still equals 1.0 times 10 to the negative 14. And this equation can be rewrite as, because we have OH negative times OH1 negative, so that become OH negative squared. And you still have this 200. And this equation, you divide both sides by 200, you get this OH1 negative square equals 1.0 times 10 to the negative 14 divided by 200. So you do the divide, you get 5.0 times 10 to the negative 17. Then you take the square root on both sides, you get hydroxide, I made a negative here, hydroxide negative concentration equals square root over 5.0 10 to the negative 17. After take the square root, get 7.1 times 10 to the negative 9. So therefore the answer is C. The next question is about calculate the pH value for given solution. In that solution, we are given the OH1 negative concentrations. So if given OH1 negative concentration and we need to calculate the pH, we can first find out the pOH, then use this equation pH plus pOH equal to 14 to find pH. By definition, pOH equals negative log OH negative concentration. Therefore, plug this given OH concentration 3.8 times 10 to the negative 9 molar, we get pOH equals negative log 3.8 times 10 to the negative 9 equals 8.42. Then we will plug this pOH equals 8.42 into this equation. We get pH plus 8.42 equals 14. Solve this for pH, we get pH equals 5.58. So therefore the answer is B. Next question is aqueous solution at 25 degrees Celsius has pOH equals 10.53. Ask which of the following is true. And we can see those choice has H plus concentration in it. So therefore we first want to find out the H plus concentrations. So to do that, from the given pOH, we can find out OH1 negative concentration by using this formula. OH concentration equals 10 to the negative pOH equals 10 to the negative 10.53. 10.53 is given. And we get 2.95 times 10 to the negative 11. Once we get the OH negative concentration, then we know at 25 degrees Celsius, OH concentration times H plus concentration equals 1.0 times 10 to the negative 14. We can use this equation to find out H plus. So to do that, we use this equation and solving for H plus. So H plus will become 1.0 times 10 to the negative 14 divided by OH negative concentration. And we just find out OH1 negative concentration is 2.95 times 10 to the negative 11, so divide. We get 3.39 times 10 to the negative 4. Then we know at 25 degrees Celsius, in neutral solution, H plus equals 10 to the negative 7. In acidic solution, H plus will be larger than 10 to the negative 7. And in basic solution, H plus less than 10 to the negative 7. And we just find out H plus for this given solution 3.39 times 10 to the negative 4, which is larger than 10 to the negative 7. So therefore our solution is acidic. And so therefore the answer for this question 4 is E. Question number 5 is order the following 3 solutions from the smallest to the largest pH. So therefore we have to use the given concentration of the acid to find out the pH. To find out pH for the 3 given solutions, we need to find out the H plus. We can see that these 3 acids, HClO3, HNO3, and HCl, are all strong monoprotic acids. So therefore, H plus concentration simply equals the concentration of the acid. And the concentration of acid are given. So therefore, for example, for solution 1, we have H plus concentration equals HClO3 concentration equals 0.0020 molar. Using the equation pH equals negative log H plus, we can get pH equals negative log 0.0020 equals 2.70. Similarly, for the second equation, for the second solution, we have H plus equals HNO3 concentration. The HNO3 concentration is given as 0.30 molar. So therefore, using equation pH equals negative log H plus again, we get pH equals negative log 0.30 equals 0.52. For the solution 3, we see our acid is HCl, so therefore the H plus concentration equals concentration of HCl equals 1.50 molar. Using equation pH equals negative log H plus again, we get pH equals negative log 1.50 equals negative 0.176. So therefore, from the smallest pH to the largest pH, we have this smallest one. This is 3, that's the next smallest one, that's 2, and the larger one is 2.7. So therefore, we have this order, which solution 3, 2, and 1. So therefore, the answer is A. Next question, question number 6. You want to order the following solution in the order of pH from smallest one to the largest one. And this few solution, one is barium hydroxide, the other one is potassium hydroxide, the other one is pure water. So we can see that barium hydroxide and potassium hydroxide are strong base, and in pure water we assume it's 25 degrees Celsius. So at 25 degrees Celsius, H plus will equals 10 to the negative 7. So therefore, for solution 1, we want to find out first of all find out the concentration of hydroxide, and hydroxide will equal 2 times the concentration of barium hydroxide. So therefore, become 2 times 0.03 equals 0.06. Why 2 times 0.03? Because these 2 is come from the subscript in the barium hydroxide. So there is 2 there, and so therefore this 2 times the concentration come from there. So we can see this there are 2 hydroxide in 1 barium hydroxide, and so therefore we're using the P scale. Using POH equals negative log OH, we get POH equals negative log 0.060 equals 1.22. For the second, then we use pH plus pOH equal to 14, find out pH equal to 14 minus pOH equals 12.78. For the second solution, we will do the same, but a little bit different because hydroxide equals 1 times the concentration of KOH. Why? Because there is only one OH in one KOH. So hydroxide 1 times the given concentration of the base because there is only one OH in one KOH. So using this equation, we find a pOH, and we get pOH is 1.05. And then again, just use pH plus pOH equal to 14, and we find pH 12.95. For the last one, for water, we use the H plus equals 1.0 times 10 to negative 7, so therefore pH equals positive 7. So therefore, from the smallest one to the largest one, smallest one will be 7, the next smallest one is 12.78, then the largest one is 12.95. So therefore, the answer is 312, which means the answer is D. Next question, number 7. You are given the pH of a solution of a formic acid solution at 25 degrees Celsius 2.38, and also give you the initial concentration of the formic acid. So this will be the initial concentration. And I want you to calculate the Ka for the formic acid at this temperature. So I think we will follow these few steps. So method to follow to calculate the Ka using pH is first write the chemical equation for the ionization equilibrium, and we start with our weak acid HCOOH plus water, produce H3O plus, then plus the conjugate base of the acid, which is COOH, 1 negative. Secondly, we write the equilibrium constant expression for this equilibrium. So as usual, the equilibrium constant should be the product on the top, the reactant at the bottom, raised to the power of the coefficient, or the coefficient is 1, so we have this Ka expression, or the formula for Ka. So then step 3 is find out the H plus concentration, use this formula. H plus concentration equals 10 to the negative pH. Then we will set up the IC table like that. So we know the initial concentration for the formic acid 0.15 molar. Those are approximately 0. Then we know the equilibrium concentration for this H plus, which come from the calculation. So we see the calculation here, Then we know sometimes we use H plus, sometimes we use H3O 1 plus. So therefore here I use H3O plus, same as H plus. So therefore at equilibrium, this is 0.00417. And so therefore the change will be the equilibrium minus initial, so therefore plus 0.00417 for the H3O plus. And both of this H3O plus, COOH1 negative are the products, and they have the same coefficient 1 and 1. So therefore if H plus has this plus 0.00417 change, and then this COOH1 negative will have also 0.00417 change. And once we know the initial change, we adding them together, we get the equilibrium for this COOH1 negative is also 0.00413. And then this HCOOH is the reactant. So if this product increases, the reactant decreases. So therefore, this will be decreases minus sign. And then decrease by how much? Depend on the coefficient. And we can see the equilibrium equation, the coefficient for all those are 1, 1. So therefore, this will decrease by 0.00417. And then we can see that at equilibrium, this becomes 0.15 minus 0.00417. Pretty much because this 0.00417 is so small compared to 0.15, we still have 0.15 for this acid. Okay, so once we know those concentration at equilibrium, the last three numbers, we can plug them into the formula for the Ka like that. So here I still write as 0.15 minus that, but there I write that. But if you use calculators, you will get the same result if you use this one, or you just simply use 0.15. So therefore, we get this number for Ka is 1.2 times 10 to the negative 4. The answer is B. Alright, so the next question, number 8, is kind of do the opposite. So we want to calculate the pH of this 0.53 molar acetic acid at 25 degrees Celsius. Not this opposite, because this time given the Ka, and we want to find out the pH. So the last question is given the pH, you want to find the Ka. So therefore, by reading the question, so this 0.53 molar is our initial concentration of the acetic acid, HC2H3O2. And we will follow these a few steps to solve the problem. So the first step, which is typical, you want to write up the ionization equilibrium. So our acid, the acetic acid, is HC2H3O2 plus water produce H3O plus, then produce this acetate. So then we will write up our equation for the Ka. So product on the top, reactant on the bottom, and then we'll set up the IC table. So we see our initial concentration for this. I didn't change this. So this will be HC2H3O2, and this will be our C2H3O2 1 negative. Alright, so in this problem, we don't know the concentration at equilibrium for any of them. So therefore, we have to use the assumption, say which side this equilibrium will go from the initial to equilibrium. We say initially there is zero product. So if you have a zero product, you cannot have equilibrium. So therefore, the reaction. This reaction for this given initial concentration shift to right to get equilibrium. So because it's shifting to the right, so therefore these two products will have plus sign, and this one reactant will have negative sign for the change. And how much plus, how much negative depend on the coefficient. So all the coefficient is 1, 1, and 1. So therefore, this will call that negative x, and this will call the plus x and plus x. So once we know the change, we can find out the equilibrium. So for this one, it becomes 0.53 minus x, and this becomes 0 plus x becomes x. 0 plus x is x. So we don't know the number, but we have some expression for the concentration of these three things at equilibrium. So we'll just substitute them into the equation for the Ka, and get this equation. So you can see initially we have concentration of H3O plus on the top, acetate on the top. Then we know H plus at equilibrium, we're assuming the x. Similarly for the acetate is x, so therefore x times x. The concentration of this acetic acid at equilibrium is 0.53 minus x. So this is the typical quadratic equation, but as you can make assumptions or make approximations as possible. So one assumption we can make is drop those x when the x is minus to some number or plus to some number. In this problem, we can drop this x here because here you have 0.53 minus x. So therefore, when we drop the x, that means we let the x become 0. So therefore, 0.53 minus x becomes 0.53 minus 0, so therefore becomes 0.53. If we do that, so this kind of assumption has a name called the small x approximation. It is valid if 100 times Ka is still smaller than the initial concentration of the weak acid. So let's check that. We can use our given Ka, so therefore 100 times Ka become 100 times 1.8 times 10 to the negative 5 become 0.0018, which is less than 0.53. 0.53 is the initial concentration of the weak acid. So therefore, we can use this approximation, which means this quadratic equation becomes a simplified quadratic equation. You can see compare this one with that one. Here is the same. The top is the same. So the bottom 0.53 minus x simply becomes 0.53. So the x is so small. So therefore, 0.53 minus x is still 0.53. Right. So we can solve this equation without using the quadratic formula, which will save a lot of time. So what do you do? So this 1.8 times 10 to the negative 5 on the left side, then on the right side, you have x squared on the top and 0.53. So you multiply over, you get x squared equals 0.53 times 1.8 times 10 to the negative 5. And then you take the square root on both sides, therefore you get this. Well, which one you multiply first doesn't matter. So you here write 1.8, 10 to the negative 5, then 0.53. Here I write this first, but doesn't matter. So therefore you multiply, you take the square root, you get x equals 0.00309. You check back into the IC table, you see what is x? X is the concentration at equilibrium for this H3O plus. So therefore, we know H3O plus can be write as H3O plus concentration equals H plus concentration. So therefore, H plus concentration is also X. Then we use pH equals negative log H plus concentration. We get 2.51. So therefore, the answer is D. So next question number 9, and you want to calculate the pH for a very complicated acid, which is oxalic acid. He has 2 Ka, so Ka1 and Ka2. And then you also want to calculate the concentration of the acid oxalate. So in this type of problems, as we learned from the lecture, we know this is a diprotic acid. So therefore, it ionizes to give 2H plus in 2 steps. In step 1, we call the first ionization. So H2C2O4 plus water produces H3O plus and HC2O4 1 negative. So then this HC2O4 1 negative in the second step ionizes again. HC2O4 1 negative become H3O plus, then lost another H plus, becomes C2O4 2 negative. So in the lecture we learn like one approximation. We say if Ka1 is 100 times larger than the Ka2, then the pH only depends on the first equation or the first ionization. So we use this approach. So which is true for this, because it's true for oxalic acid. So therefore we will only use the first ionization to find pH. To do that, we'll follow the typical method as what we did in the last question. So we'll first write up the equation to using the K1, which means the first ionization. So we start with H2C2O4, produce H3O plus and HC2O4 1 negative. And then we write up the Ka for this equation. So we have these two on the top, HC2O4 1 negative, as a product, and then this H2C2O4 as rectane. Then we'll set up the IC table as that. So again, we don't know what are the equilibrium concentration, and then we can see there's 0 and 0 for these two products. So therefore, for our initial condition, so this was saved to right. So therefore, these two on the right will have the plus and plus.